for knowing what a cone is. So I'm assuming you all know what a cone is. And we'll be talking about conic sections, which just mean when you cut a cone with a plane, the things you get, like the intersection, is a 2D thing because it's on a plane and on a cone as well. So people coming in between is kind of disturbing. Can you? Okay, no, I'll have to be the next time. Yeah, so these are called conic sections, and throughout my whole JE life, I've learned about conic sections through coordinate geometry, which is very annoying because you have no intuition as to why things are true. You just know things are true, and I've proved a lot of things, and I know they are true, but I don't know why they should be true, which I find very, I'll say, frustrating. So today I'm going to present. Okay, do you people know the question that I asked? Can you think of a widely accepted yet non-obvious theorem? So the thing, the theorem or whatever it was, it's why does slicing a cone give us an ellipse? How many of you have seen this before?
The two-sphere proof technique.
Yeah, wow, that's nice. So, okay. So this, I'm gonna also prove this. I had seen this in a 3 blue and brown video, which was very beautiful. And then I wanted to prove it for hyperbola and parabola, but I didn't do it for 2 years. I'm gonna do it now in front of you, as in I did it before as well, but yeah. But before that, I'll start with some nice properties about conics, which I like a lot. Yeah, so I'll start sharing my screen, and also if you don't understand anything at any point, just stop me and ask me. Yeah, you should be able to see my screen. Right. Okay, so we start with an animation that a senior from CMI made using Manin, which is very beautiful. Yeah. Okay. This is an ellipse. These are watching this is just beautiful. So I'm letting you people watch it. Yeah. So what I want to prove is, okay, so the definition of an ellipse that we generally know is that the distance, an ellipse is the locus of all such points P, such that the distance from the points, from the point P to two fixed points, like the sum of the distances, is constant. So for example, this y satisfies that y of 1 plus y of 2 is constant wherever you go on the ellipse. Now we have to prove that what the sum is for some random point x, either inside or outside the ellipse. So for example, we take this point, which a random point which is inside the ellipse. And now, can you see why, like, can you compare this length, this sum, xf1 plus xf2 to yf1 plus yf2? So will it be greater than or less than this one? Do you understand the question? Also, I can't, I'm sharing my screen, so I can't see you people, so it'll be easier if you can just speak up.
Less.
It's less than.
Okay, so do you see why?
Triangular inequalities.
Yeah, or the shortest distance between any 2 points is the straight line. Whatever. Sorry, that was a different reference. Anyway, so outside the ellipse, it's going to, but for if there are people who still who don't know why this is true, it's just because xf1 plus xf2, we have to compare this thing and yf1 plus yf2, right? And on if you compare these two, the xf1 part is common to both xf1 and yf1, so we just ignore it. And now we have to prove that xf2 is less than yx plus yf2, which is just true. This way. Triangle. And now, can someone tell me what this xf1 plus xf2 is going to be? Is it going to be greater than or equal to or less than?
Greater than.
Yeah. Which is because the lengths we are comparing now is it's like the same thing except y and x have interchanged places. Right. Yeah, so this is the thing for ellipse, and you can prove the same things for parabola. Can someone quickly tell the proof as to? Okay, so what we know is for a parabola, the definition is this length xf is equal to this length zf is equal to the length zy for all points on the parabola. That is how a parabola is defined. So can someone tell me how the lengths xf compare with xy when x is inside the parabola? Like zf for points on the parabola. So this is a region where these lengths are equal. Now there is some notion of being inside the region, points being inside the region and outside, right? So for points inside, for example, this is xf less than xy or greater than?
XF is
It's
one.
evident.
Less than.
Yeah, and do you see why? I mean, it's xf and xy. We have to compare xf and xy. So xf and yeah, so zf is equal to zy, and for points inside. Oh, I'm being very nervous and I'm forgetting things. I hope that's fine.
Triangular inequality.
Yeah, can you just tell improve?
Well, if you drop,
Yeah.
let's say, a perpendicular from f1 to xy, right, and you know the cosecant function is a decreasing function, right? You know that fz has to be greater than xf.
Yeah.
You can do that,
Because
right? Like,
Yeah, you can do that, but like I was trying to
yeah,
do simpler things.
I can say the simpler proof.
Yeah, please go on.
So fz is equal to zy. So xy is equal to xz plus zf. So from triangular inequalities, we will get xz plus xf is greater. Xz plus zf is greater than xf. So
Yes.
xf is less than xy.
Yeah. Okay, so this is for x inside, and what if x is outside? So yz is still equal to xz, and you have to compare xf and xy, and you can write xy as zy minus xy. I mean, yeah. Okay. Do you see why this is true? Does someone not see why this is true? Because I think if you don't, I'll go through the proof. But okay, I'll assume people will see because I don't hear anything.
Yeah, I think it's good. You can move on.
Yeah. So yeah, for a hyperbola, the definition of a hyperbola is there are two fixed points, and the hyperbola is the locus of all such points, such that all such points say y, such that yf2 minus yf1, like the mod of this, is constant. which to me seemed a very weird way to define some locus, but we'll see why it is true later. Why it gives such a nice shape later. Okay, so do you know what regions, in what region the difference of lengths will be negative, like less than this difference? And in what regions it will be greater than? Does that question make sense? Okay, I mean to say yf2 minus yf1 is constant, right? Let's call it some a. So for any y on this hyperbola, that difference is going to be constant. But if you take some x in this region or in this region, so in one, for example, like in the ellipse and parabola cases, inside the ellipse it was the whatever constant sum, it was less inside and greater outside. So can you guess where it should be less and where it should be greater?
Yeah, so the difference is less inside the hyperbola again because well you're getting closer hyperbolas to the origin.
Because
The hyperbolas are getting closer to the origin and yeah, it just kind of makes intuitive sense to me. Like maybe I can't prove it. Like maybe I can prove it, but it looks more involved than just
yeah. So the point of this is not to be able to like not to prove it. Like you can prove it, but the point is to get the intuition.
yeah. So if I go inside the hyperbola, then I'm actually getting closer to f2 and farther away from f1, which means my lengths are getting more equal. So the difference is getting smaller.
Yeah, the lengths are getting more equal. I like the so in this case it's just zero, right? The difference between. But yeah. So intuitively you get y, and you can just prove it is just triangle inequality. So I'll move on. If no one has a null. And now we come to this very interesting thing, which I'm pretty sure every one of you has seen, but this is important. So yeah. We have 2 points, f1 and f2, and we have a line. And we need to find some point on this line such that, let's call the point x. We want to find the point such that xf1 plus xf2 is minimum. And how you do it is you I don't really like why you do this is beyond me, but yeah, you just replace this, and then you know that pf2 is equal to pf f2 dash f2 prime because there it's just a reflection, and now you compare f1x plus x f2 prime with this length, and as you move x on this line, you see that the distance is always going to be greater than or equal to f1 f2 prime. So what we wanted is the minimum value of pf1 xf1 plus xf2, and for like the point which gives the minimum value, and that point is p. So far so good. Since you're not saying anything, I'll just assume you're understanding everything.
Yeah, it was good. Otherwise, I would encourage everyone to speak up more, please. It's really preferable if you do.
Yeah, so I feel like why this happened is because of the I don't know who said the law, but light has the shortest path. I think it was Newton only. So the path where you take the point of intersection with the reflection is because that's the path that light takes. So that's why.
Yeah, I mean, why does light do that? That is what I meant. Like, I don't know why exactly
Well, I mean, if
we just
for like,
copy light. I get it that we just copy light, but
I guess this might be a little tangential, but you can prove that light takes the shortest path actually using Huygens principle, right? By
okay.
actually assuming that as a point source, it radiates in all directions, and whenever it reflects, of something. Like there's a construction,
right.
but you can find it in
Right,
like
right.
most introductory physics books.
Okay.
So yeah.
I think we can move on.
Yeah.
There's
Okay.
actually some quantum electrodynamic stuff also. So the waves sort of constructively interfere where you have the shortest path and then they start to destructively interfere somewhere. I guess it's similar to the Huygens principle thing too, but that's also interesting. You can look at it.
Okay. I'll do that later. Yeah, okay. So now we have, it's almost the same question, except we have F1 and F2 on opposite sides of the line. And now we don't want this sum to be minimum because that won't make sense. We want the distance, we want the difference to be minimum. So for some point x on this line, we want xf1 minus xf2 commod to be minimum.
Minimum or maximum?
Sorry. Minimum would make sense. Yeah. Thank you for pointing it out. I tend to say such things. Yeah, so we want the difference between these two values to be maximum. And okay, so how I thought of this is because this question came right after that one, I knew that we had to reflect one of the points. And I tried the same argument, but what I'm trying to prove here, like why I am presenting this is how do you prove that this is the minimum case? Like, you reflect F2 and then the point where F1, F2 prime meets the line. So do you see why this point is the point we want? Okay, so what we want is Pf1 minus Pf2. For now, we know that this length is greater, so we will forget about the modulus. So Pf1 minus Pf2 is something we want to be maximum. It is just triangle inequality, but it is restatement, as in you just take the things to the other side of the inequality and it becomes negative. It's easier to visualize positive lengths or when lengths are being added and not subtracted. But what I do generally is I just take them to the other side of the equality. So much bigger, I know. Yeah, so xf1. This is eerily quiet, whatever. Xf1 minus xf2 is, yeah, so you just reflect f2. So now you have a nicer way to compare xf1 and xf2 because this is the reflection of the same line. And so this is a nice point because pf1 minus pf2 prime is just f1 f2 prime. And f1 f2 prime is always going to be less than or equal to, equal to in this case, but it's always going to be less than this distance minus this distance, right? Triangle inequality. Okay, so I'll assume that you all said right without unmuting. I'll move on. Yeah. So after this, what we had is, yeah, this is an interesting one, and I hadn't seen this before. As in, yeah. So you have two lines, and F and G, say, and you have this random point that is given to you. Now you want to find a point on, say, G, such that, let's call the point X, such that this distance, like this perpendicular distance from X to the other line, minus XF is maximum. Yeah, maximum. And here I'm not talking about the difference between the lengths. I'm saying X, let's call this, what is it? Okay, let's call this E, this point E. So we want an x such that xe minus xf is maximum and not the mod of it, because that wouldn't make sense, because if you go here and you just go to whatever towards infinity, you'll get this length is a lot more than this one. Okay, not really. What I'm saying is we want xe minus xf to be minimum. Can you think of? I mean, I've drawn P here, so it's kind of what is it called? Spoiler. But can you try to prove why P is the point we want, or like F could be anywhere, right? It could be, in this case, P is not the point we want. P is just ignore whatever and try to find the point P, which would give us xe minus xf to be maximum. Yeah, I need English classes. Also, it would be nicer if you all could just unmute, so that, I mean, it's easier, even if you're not saying anything. It's easier to. English is hard.
Yes,
Yeah.
just try to
Okay.
speak up if you can.
I couldn't hear that word. So you're talking about. This is better, because I closed the windows and the doors and it's very quiet. It's not only am I nervous of this, I'm also afraid of ghosts. Okay, this was better. Yeah, so xe minus xf, right? I claim that P is the point.
So I have an idea over there. So, okay, so should I tell? Hello?
Hello, yeah, we can hear.
Yeah, so x, okay, you said xc minus xf, right?
Yes.
Okay, no, then it will not work.
This is a weird question to ask, I thought, but
So we have to maximize xc minus xf, right?
yeah. Like, why do we have this? Or we'll know why we are doing this later, but for now, just. Okay, so how I try to prove this is.
A quick question.
Yeah, go on.
Xc is constant, right, for some x, and f is you have a choice of f within this vertical line.
No, F is
Yes,
the
f
fixed
is the
point.
focus.
Okay,
F is the fixed point. Like, I use F for fixed points.
Do we drop a perpendicular from F to XE to
F
prove
for
this? To prove this, I'm just giving a random idea.
Yeah, okay, so we don't have X yet. X is a variable point. We need to find a nice place for X. Like, we need to find a point which will give us the maximum length.
Okay.
The maximum difference.
We can drop the perpendicular from F to XE and the let the point of intersection of be B, let's say. Then XB will be a maximum only when it's like X is above like F
Yeah,
if,
okay.
if
Okay,
that
so I
makes
have got
sense.
this idea now. So should I tell you?
Just a minute, I'll address this one first. So we don't want to maximize XB, right? Like, XB is not XE minus XF.
Uh, no, but it will okay, yeah, yeah.
Yeah, but
Yes.
only when x is equal to p will xf be equal to or less than xb.
Just
So
a minute, someone else was trying to say something. I can't see names, so. It would be easier if you.
Saptarshi. Yeah, you can join FE, then we would have FE plus XF is greater than XE.
You
So
can join
then you
what? Sorry,
FE.
FE, right?
Yeah, then FE plus XF is greater than XE.
Mm-hmm.
So XE minus XF is always less than FE. Okay.
Yeah. Yeah.
Oh, achha, I thought hypotenuse. Okay, it will be greater than F. So, achha, that. Okay, sorry.
Like say the foot from F onto the line is Z, then you want to show FZ is greater than XE minus
Yes,
XF.
that is exactly what I was trying to do. I'm failing every time.
What is the foot of what?
Z is the foot from F
FZ
onto
is
line.
D.
F onto of F onto the line. Acha, this.
Yes, that one.
Yeah. Okay.
And we want to show FZ is greater than XE minus XF,
Yes,
or
for
FZ
FZ not
greater,
is equal to.
Z greater than XE minus XF.
or that FH plus Fx is greater than XE, but FH plus Fx is greater than XD, which is greater than XE.
So what do you claim the point is like?
The point
What you
P in the figure.
Like the point on the line, the point that we want. We are looking. So the question is, we want a point, right? That which like x is not fixed. We want a point. Uh,
I think what you're trying to claim is that XF plus FD is always greater than XC, except at P.
Except plus FD, I don't understand.
You have XF, which is a diagonal line,
Yeah.
and FD is the vertical line, which you label T. And that sum would always be greater than XC,
XC and XE.
XE, except for when X is at P. So that completes the proof, I think.
Okay, I thank you. Yeah.
Okay.
I think there's a rough idea everyone
Yeah.
is getting. So like you can state your proof because it's getting very confusing without the proper terminology and the points defined. So you can just state your proof and
Yeah. Okay. So the intuition is you can look at this, right? So what we want is XE minus XF, and XF is going to be equal to this for this. It's on the circle. And now this, yeah, so what we want is this length to be maximum, right? And as we go here, it just becomes negative, and we don't want that. I didn't just say lengths become negative. Don't do that. Yeah. So, so you and once you have the circle, it's very easy to see why this is like the length that we want is going to be maximum right here, right? Because it's going to be maximum only when the lowermost or the bottommost point of the circle is F. Do you intuitively get it?
Definitely.
Yeah, it is.
Yeah, it's clear.
Nice. I forgot what I was going to do next. Give me a minute. Okay, a minute is too much. I don't need a minute. Yeah, okay. Right, so, wait, how do I start sharing again? Yeah. Were you going to just say, start sharing again? I don't know. Yes. Yeah, so what is this? Right. Yeah, so what I want to prove here, okay, we have an ellipse and we have the foci and a random point P uh, on the ellipse. And as you can clearly see, this line is tangent to the ellipse at P.
Sorry. Please keep the language reasonable. Yeah, do not do this. Thank you.
Effort me. Um, yeah, so what I was saying is, okay, so what we want to prove is that this line, okay, so I'll show you some magic. Why are my hands shaking? Can you see my hands shaking?
No.
As in,
No, no worry.
okay. I shouldn't have told that. Okay, so did you see? I'm drawing an angle bisector of this and this. Okay. So these are the two lines. Isn't it surprising? Like, okay, it's surprising is relative, but yeah. So what I'm claiming is this tangent makes equal angles with f1p and f2p. And why should it be true? Yeah, can anyone try to prove it?
Sorry, could you repeat?
Smallest distance is like you get that by reflection.
What is the reflection property of the ellipse? Like, from the focus, from ray coming from one focus?
Okay, we don't yet know the reflection property. Like this is literally the reflection property. If you draw a tangent, these things may be
Like x is outside the ellipse, right? So f1x plus f2x would be longer than f1p plus f2p. So that
exactly.
would, yeah, make it the shortest distance, which is also the path followed by light.
Yes, this was the proof that I was, and it's so nice. Okay, so when as x moves on this line, yeah. So he just said the proof. Yeah.
Can you please
So,
repeat it?
okay. So x for x outside the ellipse, x f1 plus x f2 is always going to be greater than this constant sum, like wherever you take x to be. And it's going to be minimum only at one point, which is this. And because this line meets the ellipse in exactly one point, because it's the tangent, and we know that the minimum distance wala thing gives us equal angles because it's just the reflection. Right, does that make sense?
Yeah, it's good.
Okay. Okay. So we have this ellipse and we have this random line, and we consider what happens. Like this is some point, and we are looking at xf1 plus xf2. That is going to take a lot of values as we move on this line, but there is only one point where this length plus this length is minimum. Because this is a tangent. If it were an intersecting line, there would have been two such points. But there is just one such point. And we know that when, like, forget the ellipse and this line. We know that, okay, so compare this to the first question we had, F1, F2, and the line.
Yeah.
Right.
Yeah, exactly. It's in the same spirit, right? So
Yeah. So we know that these angles are equal.
yeah.
This. Yeah, so this is why This is an angle bisector. The tangent bisects the external angle. Okay, so this is true not just for ellipse, not just for ellipses. It's also true for hyperbola and parabola. So in a hyperbola, the can someone tell what the um, what is the word corresponding theorem for a hyperbola would be? Like here, the theorem is that a tangent to the ellipse at any point is externally bisects these two things, like PF1, PF.
I mean, it would be similar for hyperbola, except applied to each individual
Internal logic.
branch of the hyperbola rather than, right, like supposing you had one branch of the hyperbola, like let's say you have a point P on one of the branches of the hyperbola, P F1, right, minus P F2, right? I mean, sorry, the same thing would apply basically, is what I'm trying to say. Right, if you consider just the two foci, but like it would be different for each branch. I think.
No, I think
What I
you
mean,
can
am I
just
not
say
being articulate, sir?
you can just say that the tangent internally bisects the PF1 and PF2.
Yes. So the tangent
Yeah.
internally bisects PF1 and PF2. In the ellipse case, it was an external bisector, and here it's the internal bisector. So, which I find very nice. I don't know. Okay. So, what was I going to do next?
You were gonna do the same thing about parabolas.
No, I was not going to do it. Wait. Okay, like, is it clear to you why it should be true for? Okay, I'll do it. Okay, can someone give the proof why the tangent here? So, tangent.
So I need a little more time to say it very clearly, but the spirit, I guess, is that when you draw a tangent, there's exactly one point at which it intersects, and so that is your extreme point. And so because of that,
Yes, when you reflect across the line, it will
you
lie
will
on
get
it must have
was the spirit.
lied on the other line.
Yeah, it is the same as this case, right? Like this is F1, F2, and you have a random line, and you are comparing the difference of distances, right? So like xf1 minus xf2 is going to be something random, and it will be maximum only here, only at one point, and that point lies on the hyperbola. So yf2 minus yf1, as you okay, so this y will move on the hyperbola. Okay, wow. If you so if you move y on the hyperbola, then this difference like this length minus this length is going to take many values, and that value will be maximum only at this point, right, when it is on the
Quick question. What's X doing in this diagram? Is it doing it?
no, it's just a random, it's not doing anything. What did I just do?
Okay, thanks.
Yeah, it's basically the same thing that we did for an ellipse, and we are just changing like ellipse to hyperbola, external bisector to internal bisector, and the maximum length to minimum length, and the sum lengths to difference of lengths.
Okay, so maybe I can do like a nice, fairly concise proof here that if we take the tangent at y and we move along the tangent from like whatever, from like away from the tangent, and then we move towards y, then the more we move towards y, we are coming from the center of the hyperbola to the to like on the hyperbola. The more we move towards the hyperbola, the distance will increase, and it attains a maximum at y. So then we have that at y uh, that value is maximum, the difference is maximum, and we saw that when that happens, the reflection of one point lies on the line. So which means that they're essentially reflections about that tangent, which means the tangent is the internal bisector.
Yeah. So the reflection of F1 lies here.
Yeah, exactly. It lies on YF2.
Right. So does everyone understand the proof? Okay. Is there someone who doesn't understand? You can just unmute and say, what is this? You've done that. Okay, so I'll assume you all understand. If you don't, okay, I forgot again. Right. Yes. So what we know is, okay, so what we know so far is the tangent at any point bisects the angle, like the angle between focus to that point in an ellipse and a hyperbola, as is right. So this is a result I knew from doing coordinate geometry, and I had uh, proved it a lot of times. What it says is confocal means they have the same focus, they have the same foci. Confocal ellipses and hyperbola are orthogonal. Okay, so what orthogonal means is you take the point of intersection of two things and you draw tangents at that point, and they are perpendicular. When they are perpendicular, you call them orthogonal. Yeah. So the proof for this I had done with so much pain, and when you remember, like if you have this in mind, right? Can someone try to prove this? Why
Like if you join F1P, F2, from the ellipse it is the external angle bisector, and from the hyperbola it's the internal angle bisector,
Yes.
and they're perpendicular.
Right. Just one line proof, right? It is so beautiful, and okay. Does everyone
This is
understand?
very much similar to the Apollonia circle proof. It basically says the same thing about circles.
Okay.
Angle bisection, that's one thing you told, that one is internal bisector and another is external bisector. That's all. Their angles should be 90 degrees.
I couldn't hear you clearly, but from the words I heard, I think you attention.
Yeah, he just repeated the same idea.
So yeah, so this was a very nice thing. So the point is, when you don't when I didn't know all this, these were things that I had to prove using random coordinate stuff, which didn't make any sense to me. But when you know why, like when you get more insight into the structure of something, then these things just become natural. Like it was just one line, and by one line I don't mean yeah, it's natural is what I mean. Okay, so this is another thing which blew my mind when I read it the first time. Okay, so you have an ellipse, you have the foci, and x and y are x is a random point, and y is a point such that x, f1, y are linear on the ellipse. So we generally call this xy a focal point, right? So what we do here is we draw the angle bisectors of we draw the tangents at x and y, and the place where they meet, we draw a circle centered at this point, and and touching these two lines, and it turns out to be the x circle of this triangle, which if you don't remember that the tangents bisect this thing, it's very hard to prove. Okay, not very hard, but it's painful. When I saw this proof, and after knowing that, the tangents or thing. Okay, before I go on about why I like this so much, do you see why this is true? Can someone?
Yeah, it's good because the tangent at x it's gonna intersect like so xo is the tangent at x to the ellipse, which
Yeah.
means it's the external bisector of xf1 and xf2. So you
Yes.
have one extra. So the same holds for y. So you have the intersection of the external bisectors to two vertices which intersect at the x center of the triangle, opposite to the vertex you didn't get the external bisector for. So yeah,
Yes.
that's about
Yes. So okay, yeah. So you get why this gives the x center, right? And now I claim that this x circle touches the focal chord at f1. Uh, do you see why it should be true?
Perimeter is divided in half at F1, the triangle XYF2.
Sorry, can you repeat that?
And y from y the to the circle the two tangents from y like f1 and the other point
Yeah.
they need to be equal, right?
Yes.
Y f1 and f1 and same on the other side x f1 and that thing. So basically the triangle xyf2 का जो perimeter होगा that is half like y yf2 and similarly.
And so.
Uh, therefore that f1 is the common point जहाँ पे half हो रहा है दोनों side.
Okay.
So f1 has to be tangent.
Right. Yeah. So it is also interesting to note that this length, the length of tangent of f2 from tangent from f2 to this circle is equal to, like, this length is xf2 plus this length, right, which is xf1. So xf2 plus xf1 is okay. So f1, like when I'm stating the proof, f1 is the focal point. Yeah, it is the focus, and it's not on the circle. Like, it's not the necessarily the tangency point yet. So f1 is the focus, and we're talking about xf1 and xf2. So the sum xf2 plus xf1 is gonna be equal to a, the 2a, whatever the major axis, and yeah, and yf2 plus yf1 is also gonna be equal to that. People become so quiet suddenly. I hear my own pulse. Yes. So do you see why f1 is the point where this circle touches x1?
Yeah, I think people are saying yes. You can go on.
Okay. Right. Okay. So yes, we are done with all the thinking things. Okay, now done. There is one last thing that I'd like to. This is very beautiful. Yeah. So. What did I want to prove with this? Okay, what angles do you know in this figure? Do we know in this figure are equal as of now? Can someone just unmute and guess random angles? That will also be fine. I mean,
okay.
okay.
So f1 what looks like dash, I think f1 dash px and xpf1 are equal.
Yeah, wait, let me, okay. So this is an ellipse, and x and y are random points, and these lines are tangents to the ellipse at those points. And f1 prime is the reflection of f1. F1 prime is the reflection of f1 in this line, and f2 prime is the reflection of f2 in this line. Yeah, go on.
Yeah, then so it's obvious that f1 dash p f1 prime px and xp f1 are equal, since reflections, and
Yeah.
similarly f2 py and yp f2 prime are equal, again reflection stuff. I also want to say that f1 p f2 prime and yp f1 prime are equal.
Yes. So wait. So what you can also state it in a magical way. Yeah. So f1 prime. What you said is f1 prime px is equal to xp f1, and
Yeah.
this thing f2 py is equal to yp f2 prime.
Yeah.
What if I tell you these two things are also equal to each other?
Uh, uh, yeah, that would make sense.
Yeah. Do you see why?
No.
Okay. Can you try to
Okay, yeah, sure.
like not just you, anyone?
Should I say the proof?
I who?
Rohan.
No. Dude, you literally taught me this.
From the diagram, it looks like F1 dash P F2 and F1 P F2 dash are congruent. It looks like they just been rotated to
Yes,
sort of.
yes. Why?
Side congruency.
Okay, right.
Like,
So yeah, go on.
yeah, so f1 prime p is equal to f1 p, and f2 p is equal to f2 prime p, and f1 prime f2 is the same as f1 f2 prime, which is the length of the major axis. So since three sides are equal, the triangles are congruent.
Yes. Does everyone follow?
Yeah,
Okay. Is there anyone? Is there someone who didn't get this? I should have a counter. Yeah, I'll assume you everyone got it. So yeah, this observation, like reflecting f1 and then observing that f1 prime f2 is just equal to x f1 plus x f2, which is the major axis, is just nice. And these triangles are congruent, and there is a lot more to this, but I will not go into that. Will not go into it now. Yeah. So what we have is this angle is equal to this angle. And because this part is common, we have that this angle, okay, I should name f1 prime p f1 is equal to f2 prime p f2. Okay, and now we come to the most interesting part, or the part that I like the most. How do you like this?
I see. Right, yeah.
Yeah. So, okay, so why does slicing a cone give us an ellipse? Can someone who hasn't seen this before already try to answer? Are there even people who haven't seen this before?
Yes.
Oh yeah, yeah. I haven't seen. Like, I haven't seen a rigorous proof of why slicing a cone, and I like that should be an ellipse.
Yeah,
Okay.
yeah. Tried an analytic proof. It was way too long. you know.
Okay. Okay. So can you try? I can just do this. Can you try to prove it from? Okay. So this is a very hard thing to prove because
Okay, I do have an idea. Don't want to interrupt
just a
you.
minute, just a
Yeah,
minute.
yeah, sure, sure.
So you have this cone and you slice it with a random plane, and then you claim that this random circly ovally thing that forms follows the nice property that it has two foci and the sum of distances thing is constant, which is very. Why would you do such a thing? Like, how is that even true? It was very. Okay, so this person called Dandelin, I I can't pronounce his first two names. He was a magician. He added these two spheres. He was like, okay, let me add this sphere which is tangent to the cone and the plane. And like these two spheres are tangent to the cone and the plane. And we guess, like we don't know yet, but we guess that the points where they are tangent are nice points. And yeah, so these spheres. Oh yeah, okay. Someone was saying something. You can go on.
Yeah, no. It's very non-rigorous. Though you just ignore. I was just trying to say that if we, since we know, since it's actually kind of obvious that if the plane was actually parallel to the plane of the base of the cone, then it's
Mhm.
circle. That is very obvious. That since these are right circular cones, so if I slice them parallel to their bases, then the things that will come out are circles only.
Why is
So
it
if I have
obvious?
a, huh?
Why is it obvious? I mean, it's intuitively clear, but
It's by virtue of how you define the cone, right? Like the cone is
Yeah,
basically
yeah.
all
If
r
it's
such
right
that
circular,
r cos theta,
exactly,
right?
exactly.
No, no, no,
Like the
no,
I mean,
magnitude of
r
r
cos
don't.
theta. You
is
don't need r cos
so theta is
theta.
the angle of the cone opening or not.
No,
That's what I
No, no,
no,
mean.
no.
no.
Okay, let's say arguments.
Yeah, I'm just going to. So I'm going to assume this is a right circular cone. So if I have a plane parallel to the base of the cone, then I'm essentially just sort of starting at the center of the cones, and then I'm going down, and I'm just sort of looking in a horizontal manner. I don't know. It's kind of maybe the actual proof will be harder, but I'm sort of taking this as a given. Like so, in that sense, that again, very non-rigorous, but maybe. So if I have a and I'm claiming that if I have arbitrary intersections, so if the plane is not even parallel to the base, then at least I can sort of think of a like a projection of that plane onto a plane that is parallel. So then I'm getting that whatever the intersection of that plane with the cone is, its shadow onto like a parallel plane will actually be a circle. So whatever way we could characterize shadows is maybe, and they're nice things. So I could claim that the only kind of objects that could have a circular shadow are ellipses. Again, very non-rigorous stuff, but you clearly had a point there, so you should just go ahead with what you wanted to do.
Can I
Um,
just make a small comment? Yeah, about the shadow thing, like that is how the projective results, like how we talk about projective geometry preserving conics actually come up.
Oh,
Just a
okay.
small comment. Yeah.
Okay.
Sorry. Go
Okay.
ahead. Yeah.
why would you say so? So
I have a claim like it is not related to the proof
okay.
that is the that sum f1p plus f2p equal to the sum of the radii of two spheres. Like just
No, it's not equal to radii, sum of the radii. It would be interesting. Okay.
Probably, am I audible?
Yes, yes.
Yes, that dotted yellow line plus that white line, that's the sum. That's why it's preserved. That is what, and where the plane is intersecting, plane is touching the above sphere and the bigger sphere. Those are the so-called. That's why I think it's defined. The focuses are defined. That's and since that length is as you said, we can cut that plane. I mean the tangent to the spheres are from a point are equal, uh,
Yeah,
and
okay.
that's getting preserved.
Yeah.
And we
Uh,
are again reaching the definition of ellipse.
so could everyone hear what you said?
No, not really.
That's nice. So can you try the proof on your own?
Okay.
Yeah. I mean, this introducing these spheres was the magic trick. And like yeah, so what all do we know now? We know that this plane is tangent to the spheres. And we also know that the cone is tangent to the spheres. Right.
Yeah.
And the cone is tangent to the spheres, to the sphere at this circle, and this is the circle where the cone is tangent to the sphere, to this sphere. Okay, so what do we know about tangents to a circle from a point? Like, what do we know about tangents?
They have the same length.
Yes. And what about a sphere? Like, if we replace the circle by a sphere?
Same
They
thing.
still hold, right?
Right.
Yeah.
Yeah. So, so a general thing in geometry is, don't kill me if I say something wrong, but yeah, it is to see why, something should be true, and the proof is not the main thing. The proof just follows, and what I try to do is, what do I know about this? And
Okay, I
then
think
try
I
to
have to. Again, don't want to interrupt you if you're saying something important. I'm immediately going to shut up, but yeah, yeah. I have proof though. I got it.
Okay, go on.
Yeah, now that they explain it,
Yeah,
pretty
yeah.
apparent. But
I wasn't even looking at the two dotted circles there. I don't know why, but now that I do, it's actually nice. So you've also like drawn the lines that I need to look at. Again, I don't know why I didn't see it. So the thing is that the if I consider arbitrary point on the intersection of the plane with the cones, then I can actually see that the point where, since the spheres are tangent to the plane, where they are tangent to the plane, if I draw a line from the point, from any point on the whatever shape that is,
Yeah, you
to the
can use
point
the
where,
names that I used here too.
yeah, I can't actually see the labels, so
Oh, I'm
that's
so
right.
sorry. So, right. This thing got stuck. Okay, so
ln, that line is ln basically, like the one whose
Right,
length
right.
is constant, right?
If only
Yeah.
I could know where
you're not
the
supposed to state it like that.
Huh?
so, no, wait. Where is it tangent to the? Where is the plane
Okay,
tangent to
okay.
the sphere?
F1 and F2.
Those are
Right,
F1 and
right,
F2. This is
right.
F1,
So
this is F2, this is N,
got
this
it,
is
got it.
M, this is P.
So clearly, and okay. So then PF1 is equal to PN because, well, equal tangents to the same sphere.
Yes.
And similarly, PF2 is equal to P. I want to say L
Yeah.
because again same thing. So PF1 plus PF2 is PN plus PL, but that's a fixed constant which is Ln.
Okay, why is it a fixed constant? Why is this a straight line? It does look like a straight line, but
Uh, it's a good question. I don't know. Oh,
it
it's
just,
it's along the cone, right? So
yeah.
along the yeah, so cone is
So Ln actually passes through this
yeah.
point. Did everyone follow? Okay. Is there someone who didn't follow? Do you want me to repeat? Hello, hello.
I think someone is saying yes in the chat, so you should.
Are you don't see yes in the chat now? How am I supposed to see the chat? Oh,
Yeah,
okay.
please speak up if there's any issue.
One sec. I'm not sure how you prove that. You know, okay, the cone is touching the circle in an infinite number of points, but but the length of Pn is equal to Pf1 in only one point, which is the closest point. I'm not sure how you prove that. That would be the particular tangent. What I'm trying to say is the cone is tangent to to the sphere in an infinite number of points. Um, and I'm not sure how you prove that Pf1 would be exactly equal to Pn and not some other point around that black circle.
Yeah, so what the point n is such that uh, Pn is actually tangent to the cone, like it's along the cone. So if I draw this Ln line or Pn, or if I draw the line Pn, it passes through this.
Okay.
So it is a straight line. Otherwise, it would be a curved thing, right? If it were
Oh,
not.
yeah, that's true. I see that.
So that is why Pn is okay. So someone wanted me to repeat. So observe that this. So what do we know about this point P? It lies on the plane as well as on the cone. So because the plane is tangent to the sphere, we have PF1 is tangent to the sphere. Because the plane itself is tangent, so any line passing through the tangency point would be tangent. And we have Pn tangent to the sphere because Pn is nothing but this line that would, like, you if you draw a line from this tip to P, it's like the angle it makes is exactly the angle that the cone makes. Can you see it? Whoever wanted me to repeat. But, okay, I'll assume you do.
Actually, nobody wanted you to repeat, just for.
Yeah, the person who asked on the chat was actually saying yes to something else, but
Okay, okay. Thank you. Yeah, so this is a very nice proof, and yeah, so these spheres are called Dandelin spheres. Did I mention that already? I
you
guess not.
mentioned that Dandelin came up with the idea. I'm not sure if you said that the spheres themselves are called Dandelin spheres. I know it's a minor technicality, but yeah.
I mean, this is such a, like, it looks like a very simple thing after you have the spheres, but coming up with the spheres was such a nice, it was such a magical thing that the spheres are named after them. Okay. So can you try to prove the same thing for a hyperbola? Do you remember what the definition of a hyperbola is?
Like the plane cuts through the other, like one in the upper part and one in the lower part, something like that, I guess.
Yeah, basically the angle is so much that it cuts. Yeah,
Both the sides.
so much. Wow. Yeah, right. So that is one definition. What is the other definition? For example, in an ellipse, we had the sum constant.
The difference is
And
constant.
difference constant.
Yes. Okay, so I have a nice diagram to spoil the proof for you. Sorry.
Remember the plane, we will just tilt the plane so that the plane we are considering that we are trying to ellipse, we would just tilt the plane to get a hyperbola. And after a
Yeah,
certain angle, that would actually determine the eccentricity of that.
yeah, we can actually tilt the plane, but it becomes very small, so it becomes too small, so I made it.
Yes, on the either side. Yes.
Yeah, this is exactly
And
what.
this thing actually also would probably give the asymptote, like some the asymptotes of the hyperbola. That two, um, if you cut the cone along the plane along the vertical height, then then those things we would also probably get about the asymptotes of the hyperbola element.
It's hard to understand, comprehend what you're saying. Like the voice is very. Uh, is that so for me or is it so for everyone?
No, no,
No, the
no.
voice was not clear for me
Yeah,
either.
Yeah, it sounds a bit muffled.
yeah.
Yeah, can you type in the chat or something and then if it
Uh,
is worth typing like, sometimes as in not if you really want to type is what I mean because sometimes I say stuff and then for typing it's like no so much my I won't do it. Yeah, okay. So this is a hyperbola. Isn't it beautiful? Okay. Right. Yeah, so what is the difference? Okay, what we want to prove is PF2 minus PF1 is constant. Like we are guessing that F1 and F2 are the foci, where like F1 and F2 are in fact the tangency points, like the points where this sphere meets the plane and this sphere meets the Can someone tell me why this should be true? Yeah. Do you people see why this is true?
Yeah.
Yes.
But
Okay.
pretty much a copy paste of the last one.
Yes. Can someone just go over the proof once?
See, again, the labeling is not very visible, so that's
Right, just use random names. It's fine. Like F1 and F2, you know, are the foci, right? And this is P. The variable point on the hyperbola is P. Hello, hello.
yeah, it's a little hard to
Assume
see.
this to be M and N. Like, it's fine. Yeah. Okay. So suppose this is M and this is N. And if you want me to tilt the figure in a different way, just ask me to, so that things are more visible. I don't know.
I don't think any particular orientation will bear that many benefits. It's fine.
Okay. Oh, yeah, go on with the proof. Someone wanted to say, I mean, someone wanted. Okay, it doesn't matter who wanted. Who wants to speak up? Hello, hello. I need English classes.
I think you should do it because you're more familiar with the figure.
You think I should tell the proof or join English classes?
Yeah, that's what he said. You should just do the proof.
I mean, someone can do it, right? I want to ensure that.
Ari, see, the issue is that what exactly MNNR is not very clear directly.
It's fine. Just see, and just use any
No,
name
no,
you
no.
want to just stick to
Not,
it.
it's not a name issue. It's what MNNR.
Acha. So yeah, okay. So this is a cone, as you can see, and there's a plane that intersects the cone in such a way that it forms a hyperbola. And we want to prove that it forms a certain UN kind of thing. And we want to prove that this UN kind of thing is actually a hyperbola, which means that it satisfies a property that for any point on the hyperbola, for example, P here, it is true that PF2 minus PF1 is constant.
Right, could you just say what F1 and F2 are, like with respect to the pier and the cones and everything?
Okay. So, do you remember what F1 and F2 were in the previous?
Yeah, it's where the plane is tangent to the two Dandelin circles,
Yes.
even in for the hyperbola case, right? So
Yeah.
yeah.
So they are the same things. Like the small sphere is tangent to the plane at F1, and the larger sphere is tangent to the plane at F2.
Okay, yeah. I guess it is a similar proof to last time, right? Like these two white lines are equal. The two green lines are, also equal. The what is the labeling? Sorry, for the
Just use
bottom.
your labeling. Suppose this point is M and that is N.
Okay, M as in where it passes through the what do you call that cusp like thing,
No,
right?
M is where the circle, the tangency circle.
Ha, yeah, yeah. Okay, okay, right. So let yeah, okay. So let P is the point on the hyperbola, right? Okay, so yeah, so PM and PM plus MN, right? That's constant because sorry,
What is constant, sorry?
what? No, 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 I'm very sorry. Sorry, that white line, right? Sorry, M to N is constant. Yeah, M to N is constant because it's along the cone, right?
Yeah.
It's passing through. What is that thing called where the two halves of the
We
cone?
call it tip.
The apex. Just
Whatever,
go.
the apex, right. So m to n passes through that apex, right? And each of those two different things is always constant. I think you get why m to n is constant, right? Like I'm not able to
I didn't
articulate it
get
so
why it is
clearly.
constant.
Let
I
that
mean,
like let's search for
Yeah,
it.
yeah.
yeah,
Anyway,
I mean, it's the
and
same
then
reason, right? Like,
see, okay, there is a nice way to state this. Let's call the tip
okay,
T.
okay,
So,
the tip, yeah, yeah, the tip.
it
So
is
mn, yeah. So basically,
MN,
mn passes through the tip of the cone, right? Sorry.
MN is just TM plus TN, and TM is just the length of tangent from T to this small circle.
Okay, yeah. So T is the tip over here. Okay, fine. Yeah. So this thing, right? Mn, right? We basically just have to prove that pf1 minus pf2 is equal to mn over here,
Yeah.
right? So, oh, okay, right. So yeah, can I just yeah, I'll just continue. So,
Yeah.
so we also know that PM, right? Yeah. We also know that PM is along the cone. It's along the, the same line. It's along that same MN line, right? So, and we know that PF1 is equal to, what is that? PN. Yeah. We know that
Yeah.
PF1 is equal to PN, right? And we also know that
Why is PF1 equal to PM?
sorry, PF2. Oh man, yeah, PF2 is equal to PN, right? And then PM is equal to PF1. And we know that MN is constant.
Okay, so
So,
what you're saying is this length
yeah,
is equal to this length because they are tangents to the sphere.
yeah,
One
yeah,
is along
exactly.
the plane and another is along the cone.
Yes,
And
exactly. Yeah,
similarly, this white length is equal to the white length
yeah,
because of
exactly.
the
Yeah,
exact reason. And
yeah,
now the difference is just Pn minus Pm,
yeah, which
which
is
is just
MN.
yeah.
Yeah,
And as you like, whatever point you choose on the hyperbola, Mn is going to be constant.
right. Yeah,
Yes, it
exactly.
is equal to Tm.
That's what I meant. Yeah.
Does everyone follow?
Yeah.
Oh, this is insane.
I know, right?
Yeah. Like, wait, is there a lot of modern day mathematics where these kinds of arguments come up a lot? Like, I mean, I'm like really crazy stuff like this because all I've seen is like, okay, just throw an analytic proof at this. But
Yeah. I think the good thing about analytic proofs is that even though they're boring, they're at least efficient, so that you can come up with them with lots of effort. But these
Okay.
are, yeah, but these are
Yeah,
obviously not
yeah. Magic is obviously the most superior thing.
Yeah, exactly.
yeah. No, for people like me who are bad at geometry, analytic proofs are very attractive. But
Yeah.
yeah.
I mean,
Don't do
were you able
analytic
to
proofs
obviously
of
guess?
anything.
Sorry?
Even in analysis, don't do analytic proofs. It's fine.
What the hell?
Okay. I think I should go bring my charger. I'll be back in half a minute. In the meanwhile, you can try to think why this is true for, oh no, where did it go? Oh no, yeah, for an ellipse,
For parabola.
for a parabola.
Yeah.
Okay, so just so you know, a parabola is formed when it is like the thing between ellipsis and hyperbola. So when you have the angle of the plane that is intersecting equal to the angle of the cone, the slope, when these slopes are equal, you have it, but you have a parabola. And what the normal what the definition of a parabola is? It's that PF1 is equal to this line. This is the perpendicular line to the direction. This is the random line which I'm calling the direction. I'll be back in the chart.
How does the directrix come to slicing?
How does the directrix work?
Come like, do we find it manually or we get it
Uh,
automatically
the
also?
the the directrix is the intersection of the plane of the parabola and the plane of the circle where the sphere is tangent to the cone.
Hi, I wasn't here, sorry. Hello, hello.
Hi.
Yeah, I'm back. Yeah.
No, but
So
like,
someone was asking what the directrix is, right?
yes.
Or no?
Yeah, someone did tell that it is the plane of that circle, but you do not have that sphere also, no? Before this construction.
Yeah, yeah. We didn't have the sphere. Like we first. Okay. How do you define the directrix without the sphere? It is this distance is equal to this distance. Then you draw a perpendicular line.
Yeah, got it.
Like in this plane, that is the directrix, but it also happens to be in the same plane as this circle. Does that make sense?
Yeah.
Okay, nice. Okay, so proofs. Do you see why? Okay. Does anyone see what do we want to prove?
We
Can
want to
someone just?
prove that the distance of the point from that circle is equal to that uh, length to directrix.
In the original problem, we want to
From the
prove
proof.
that PF1, yeah,
Yeah.
PF1 is equal to PM. Is that N? No, it's L.
Yeah, but like PF,
PF1 is equal to PL.
yeah, but also PF1 equal to that PN because of tangency.
Right. So now we want to prove that Pn is equal to PL. Do you know why that is true? Do you see why it is true?
I have a question. Are we given that the line and the circle are in the same plane? Or do we need to prove that separately? Because that seems quite irritating to try and prove.
We wait. We can try.
Unless, of course, that's not required for the proof that you
Yes.
have in mind.
Yeah, exactly. It seems like it would be the you can like it'd be easier to draw the plane once you prove right that this thing is a parabola or that the distance from the directrix to the curve is equal to the distance from the curve to the point of tangency, right? Once you have that down, it would be easier to then draw that plane and say that the cross section is a circle rather than the other way around.
What was the last part of the sentence?
Sorry, like it would be like easier to construct the plane and say that like where it cuts the circle is another, like the sphere is another circle, rather than like starting with the plane, right, and then trying to prove that that plane cuts a circle. I mean, I don't know.
I think what
Yeah,
the
I think we
plane
can come back to this point later.
I think what the plane
I'm
is
really
actually.
sorry, but I don't know what that yellow plane is because I just kind of went missing for one second. Could someone just define?
What is green versus sorry, go on.
Yeah, whatever the yellow green plane thing. What is it? It's like how did we define it?
It's the plane of the circle of intersection.
Yeah,
Plane
okay.
of
It's yeah. We don't know that this line is the directrix yet. It is just a random plane. It is just a plane through the circle of intersection. Yes. But we are guessing that this is the directrix, like how we were guessing that this is the focus, the place where
no,
the circle.
no. See, I don't. The part that I don't get is uh, how did we get the yellow plane or the green plane, whatever?
Yeah. So the line. Okay. This plane is yeah. So this plane is
Plane of the circle of tangency.
yeah. I mean,
Oh,
what
okay,
do you
okay.
mean by
Oh,
what did
okay.
we get?
No. I was just missing on the yellow plane was.
How is it defined?
Yeah. How did we? Oh, now I get it. So it's the circle of tangency of the sphere with the cone, and we just take that plane, right? The plane of that circle, and we let it intersect with the plane of the parabola, and we claim that
Yeah,
that's the direction.
it intersects the other plane.
Right, right.
And this is the line that we would like to read the directrix. So, okay, can someone come up with a proof for this?
We can draw the normal from that point on the plane, and then we can use the parallel thing that this angle is equal to this angle, and then prove that this is isosceles.
Okay, so if you look at it from above, this is not going to be an isosceles triangle, because what you're saying is this PLN is an isosceles triangle with the normal, like the normal is just a midpoint. Your audio
I
is clear. I could make out what you were saying because I had the same thoughts before, but okay, so what you're saying is, what I'm saying is, if you draw the normal from P, the point would be like from this view, it would be right above P, and it wouldn't be the midpoint of MN. Like if it were the midpoint of MN, then you just have that that it's an isosceles triangle. Well, I mean, you have to prove it.
think I have a proof.
Okay, go on.
So Fp is equal to Fn. That is kind of obvious. Like tangents to the sphere, and
F equal to PM, yeah.
yeah, sorry, Fp is equal to Pn, and the darker plane has like the yellow line along the darker plane has the same angle from the vertical, the axis of the cone, as the yellow line that like as Pn. So if you like the projection of both of these lines along the axis is the same, and the angle they make from the axis is also the same. The lengths of both the lines are the same.
Yes. Okay. So yeah. So when I was trying, wait, does everyone follow?
No, I actually didn't follow.
Okay. Actually, it is more rewarding when you yourself are able to see the proof. Which is what I mean.
Perpendicular, na, basically. That guy was saying for. You drop a perpendicular from P to the green plane, and then you measure triangles, do some trigonometry, and you will get.
No, I was talking about the line which is perpendicular to the green plane. If you project both the lines, both the yellow lines on the axis of the cones, they would have the same length.
Yeah, why?
That you could also say in this way, like you drop a perpendicular from P onto the green plane. You say that that line has equal angles with both the yellow lines, and then you
What do you
just
mean by
Yeah, yes,
that
yes, yes,
line has, okay.
yes, exactly.
What we're saying is this angle is equal to this angle.
That is what I meant. The,
And why is that?
uh,
they have equal angles, and the length of the perpendicular is the same. So, like, just
they,
trigonometry.
they have equal angles because the darker plane in which the parabola is, it has to be at the same angle as the opposite side of the cone, right? Otherwise, it would cut again or it would make an ellipse.
Yeah. Okay. Yeah. So yeah, what you're saying is this slope. Okay. This
Basically,
angle.
the perpendicular line is
Oh,
parallel to the axis,
Yeah,
and
it's
axis makes the same
yeah.
angle with both the
I
Yeah.
think what I'm
It is
trying to
very
say.
useful to be able to see this. So
They make the apex angle.
Right. Yes, exactly.
yeah.
Both of them make the apex angle because the plane is at the same angle as
To
any
the
line
vertical.
from the apex, That's which is the angle between the gray plane and the vertical, and similarly the line is at the same angle.
Yeah. Got it.
Okay. So does everyone follow?
Yeah.
Is there someone present? Why do people suddenly mute themselves?
So it's not even necessary that the vertical is in the same plane as the two yellow lines, right?
It's not in the same plane. It doesn't have to be, right? Right?
Yeah, definitely.
It's like this plane is not even perpendicular to the.
So how are the angles equal? I didn't get that.
Yeah. So okay, for the angles, look at this diagram from here. From here. So this is when the line that we wanted is on this side of the cone, like it's on the side of the cone. Do you get what I mean by this side of the cone? Like if you take this plane, if you see what, oh, okay. So in this plane, everything is within this plane, right? This pink line and, is it pink? Yeah. The pink line, the yellow line, and the border of the cone are in the same plane. The border, yeah, the border.
What do you mean the border of the cone is in a plane?
As in, right. So if you look at it from here, you can. Okay, what am I saying? What I mean to say is, look at it from such an angle that this yellow line is like it is in this plane. Okay, so if you take this plane that passes through the tip of the cone and the plane of my laptop or the plane of the screen, does that make more sense? No? Sad. So,
You can assume it does if nobody's responding because, yeah.
yeah. Okay. So the plane of the laptop now, okay, at this point the yellow line is not in the plane of the laptop. It is like closer to me, right?
The
And
line F1N, right?
sorry,
The line F1N. Oh, PN, sorry.
the line PM, yeah. Yeah. The line, this yellow line PN is not in the plane of the screen. I'm asking you to look at it from such an angle that it is in the plane of the screen.
Yeah.
And because
Can you
P
just
is,
repeat the
sorry,
Can you just repeat the definition of parabola? I was just disconnected. The
which
beginning
one?
part. No. I was confused with the focus and the plane by which you're talking about.
You want me to repeat the definition of a parabola or
Yes,
what do you
actually,
want?
because
Okay, so a parabola is defined as the locus of all points such that all points P such that Pf1 is equal to the distance of P from a fixed line, the perpendicular distance of this point to this line. Like if you have y is equal to x squared plus 2, okay, let's not talk about it.
with the distance.
Yeah, so the distance of every point of the parabola from the focus is equal to the perpendicular distance. Does that make sense?
Can you just tell me where is the point of focus? Like I was.
Okay, let me. Yeah. So now we are in the plane of the the plane of the screen is is the plane of the parabola. So all these points P satisfy that Pf1 is equal to this line. If we had a point say here, then this F1 would be equal to this perpendicular distance. And if you had a point here, then this F1 is equal to this distance. Does that make more sense?
Yes.
Right. So, do you get why this angle, like this 2D angle, is equal to this 2D angle?
Maybe if it is not, we can leave them at a point of suspense and they can try to figure it out.
Yeah, it's just like you don't need to prove anything. It's just look at it from this angle, and from this side, you know that this angle is equal to this angle, like
Yeah.
in 2D, not the solid angle, this angle in 2D. And now you know, if you look at it in such a way that this triangle is in the plane of the screen, then this angle is actually equal to 90 minus this angle. This angle, as we know, is equal to 90 minus this angle because it is parallel to the side of the cone.
Yeah.
Any questions?
How do we make these in GeoGebra?
How to?
Make these shorter in GeoGebra.
Oh, this. Oh, I have no clue. So yeah, I should credit. I forgot the name. Andreas Lindner. I actually used like these things were already made. Wait, I'll show you what I used, or that could be a bad idea. Don't ask me why it's in random. Yeah, it was a bad idea.
You can share the references and the links and we'll post it in the server. I think that would be more convenient for everyone anyway.
Right. Yes. Yeah, I can share the. Okay, so all that I talked about today was all the knowledge of that I shared today came from this book by Apopian and Zaslavsky. Yeah, that is how you pronounce it. The book is called Geometry of Conics, and it is a very awesome book. You people can refer to it. Yes. And and the diagrams, I used a kind of template from GeoGebra, and there are a lot of things in resources under resources in GeoGebra if you open it, and not all of them can be used, but this person Andreas Lindner made this thing that could be used. So I just changed the colors to make it look nice. I hope that answers your question. Any other question?
Not a question, but Dandelin's magic is a nice description.
Thank you.
It's very nice. The proofs are very cool and magical.
Okay, thanks, Pranav. Yeah. If you want to talk about this further or anything for that matter further, you can contact me, or if you have nice results or anything interesting. Basically, if you want to contact me, you can contact me on my email ID, which I'm entering in the chat. I'm using my CMI email ID. Anything else you want to say, or you can? Right. Yeah, it's 8:39. We're 9 minutes over time, I guess.
Yes.
If you people don't have any questions or anything to say, we can close, I guess.
Okay, nice. I'll stop the recording now.
Oh, Pranjal is here. I didn't know Pranjal was here.
Hi.
Hi.